All right, if you're studying psychology, sociology, or really any field that deals with research, you know the feeling. Statistics can feel like you're learning a whole new, kind of confusing language. Well, in this explainer, we're going to hand you the ultimate survival guide. We're going to decode these numbers so you can walk into your next exam feeling totally in control.
Does a line of text like this just make your head spin? Yeah, I get it. It looks like some kind of secret code. But I promise, by the end of this, you are going to know exactly what every single piece of that means. We're going to break this whole thing down one step at a time so you can read it like a pro.
Okay, first things first. Before we can jump to any big, grand conclusions about the world, we just have to get a handle on the basics. We have to be able to simply describe the data we collected. You know, what actually happened. This is the groundwork for everything else.
So statistics really come in two main flavors. Over here on the left, you've got descriptive stats. These are super straightforward. They just tell the story of the data from your specific group of people. But the whole point of research isn't just about your little sample, right? It's about the bigger picture. And that's where inferential stats on the right come in. They help you make an educated leap, a conclusion about what your results might mean for the entire population.
The most common place to start is the mean, which is, just the average. If Group A has a mean happiness score of 7.2 and Group B has a mean of 5.8, then you know that, on average, the people in Group A were happier. It's really as simple as that. But, the average never tells the whole story. That's where the standard deviation, or SD, comes in. It tells you how consistent the scores are. A really small SD means pretty much everyone's score was huddled up right around that average. But a large SD, that means the scores were all over the map.
And this is a great way to see it visually. The height of the bars, that's your mean score. So you can see Group A is higher. But look at those little lines on top. Those are called error bars, and they represent the variability. See how Group B has a way bigger error bar? That tells you, at a glance, that its scores were a lot more spread out than Group A's. Okay, so we've described our data. We saw that there's a difference between our groups. But here comes the million-dollar question. Is that difference actually real and meaningful? Or was it just a random fluke? Did we just get lucky with the people we happened to test? Answering that is the job of inferential statistics.
Our first tool for this job is the confidence interval, or CI. Now, look, since we can't test every single person on the planet, our result is always just an estimate. The CI gives us a range of plausible values for where the true population mean probably is. So a 95% CI is our way of saying, hey, we are 95% confident that the real average for everybody is somewhere inside this range.
This is a perfect way to think about it. A narrow confidence interval is just like hitting a bullseye. It means your estimate is super precise, and you've really zeroed in on the true value. But a wide interval? That's like your shots are all over the target. You're much less certain about where the center actually is.
So, what makes that interval narrow or wide? Well, it's mostly two big things. First, your sample size. The more people you test, the more precise your estimate gets, and the narrower that CI becomes. Makes sense, right? Second is the variability in your data. If your scores are all over the place to begin with, your CI is going to be wider to reflect that uncertainty. And next up, we have the famous, or maybe infamous, p-value. Think of it like a courtroom. We start by assuming the null hypothesis is true, basically that our treatment doesn't do anything and there's no real effect out there. The p-value tells us the probability of getting the data we got if that no effect idea is true. If that probability is really, really low, and the magic number is usually less than 5%, or p less than 0.05, we say, you know what, that's too unlikely. We reject the no effect idea and conclude our finding probably wasn't just a random fluke.
Okay, now for the really cool part. This is where it all clicks together. There's this incredibly powerful shortcut that connects confidence intervals and p-values, and for an exam, it is an absolute game changer. Let's call it the golden rule. Seriously, think about it. What if you didn't even have to hunt for the p-value? What if you could tell if a result was significant just by glancing at that range of numbers from the confidence interval? Well, turns out you totally can. And here it is. This is the key. When you're comparing two groups, you have to look at the confidence interval for the difference between them. If that range of plausible values does not include the number 0, then congratulations, your result is statistically significant. Why? Because a difference of 0 means no effect. And if 0 isn't a plausible value in your range, then there's probably a real effect going on.
Let's see this in action. It makes it so much clearer. So let's say the average difference between our groups is 1.4. And the 95% confidence interval for that difference goes from 0.6 up to 2.2. Just look at that range. Does it contain the number 0? Nope, not even close. Boom. That means this result is statistically significant.
Okay, but now look at this one. The difference is 0.4, but the confidence interval goes all the way from negative 0.3 up to positive 1.1. So since this range crosses right over and includes the number 0, it means that no difference is a totally plausible outcome. So, this result is not statistically significant.
All right, so now we know if a difference is real, statistically significant, and not just due to chance. But there is one last crucial piece of the puzzle. Is that difference actually big enough to care about in the real world?
And that is exactly what effect size tells you. It's a measure of the magnitude, the practical importance of your finding. See, statistical significance just tells you if there's an effect. Effect size tells you if it's a huge, life-changing effect or a tiny, barely noticeable one. A really common way to measure this is with something called Cohen's d, and you can just think of these numbers as benchmarks, kind of like small, medium, and large. A d around 0.2 is considered a small effect, 0.5 is medium, and if you see something around 0.8 or higher, that's a large and probably pretty meaningful effect.
Okay, we have covered all the key concepts, we have all the pieces on the table. Now let's put them together into a simple, step-by-step playbook you can use anytime you see a research result on an exam.
Here it is, your 5-step playbook. Anytime you're faced with stats, just walk through these questions. 1. What do the means even tell you? What's the basic story? 2. How precise is that CI? Is it nice and narrow or is it super wide? 3 and 4 are your significance check. Use that golden rule. Does the CI for the difference include 0? And then double check that the p-value is less than 0.05. And finally, step 5. Look at the effect size and ask the big question. Is this difference actually big enough to matter?
The most important thing you can take away from all of this is actually a shift in your mindset. Stop trying to just memorize definitions like, what is a p-value? Instead, start asking, what is this p-value telling me about the data? These numbers aren't just facts to recite, they're clues to help you understand a story.
And I'll leave you with this final thought to chew on. If you have a huge sample size, like thousands of people, you can find a statistically significant result for almost any effect, no matter how tiny and unimportant it is. So the real question is, if an effect is technically real, but it's too small to have any practical importance, does it actually matter? Answering that is what separates just passing the class from truly understanding research.